Okay, let's talk about one of the most, and I mean most, important steps in any machine learning project: splitting your data. Seriously, if you get this right, you're on your way to building a model that actually works in the real world. But if you get it wrong, well, you end up with a model that looks amazing in your notebook, but just completely falls apart when it actually matters. So how do we make sure our models are truly learning and not just cheating?
So, let's start with the big problem we're trying to solve here. I mean, if you've got this huge data set, why not just throw all of it at your model? More data is always better, right? You'd think so, but it leads to what I like to call the memorization problem.
Think about it like this. Imagine you're studying for a big exam. You get a hold of some practice questions, and you just memorize the answer to every single one. If the final exam uses those exact same questions, you're going to ace it, a perfect score. But did you actually learn anything? Or did you just memorize the answers? Well, machine learning models can fall into that exact same trap.
And this slide just nails the difference. On one side, you've got a model that's just memorized everything. We call this overfitting. It's like that student who gets 100% on the practice test, but completely bombs when the questions are even slightly different. On the other side, you have a model that understands. It can take what it's learned and apply it to new problems it's never ever seen before. That is the goal. That's what we're aiming for.
So here's the bottom line. We split our data to simulate the future. We have to hold back a piece of it to be a totally fair final exam, a stand-in for the real world. This is how we test if the model can generalize its knowledge, not just spit back answers it's already seen. So how do we actually do this? How do we set up this fair test? Well, we give our model a structured study plan, and that plan involves 3 different data sets. Let's break them down. First up, you've got your training set. Think of this as the textbook, the lecture notes, all the homework assignments. This is the biggest chunk of your data, and it's the stuff the model actually gets to study to learn all the patterns and rules. Next is the validation set. This is your mock exam. You use it to check your progress and maybe tweak your study habits. For a model, this means tuning all the high-level knobs and dials. We call these hyperparameters to see which combination works best. And you do all of this without ever looking at the final exam questions. And finally, we have the test set. This is it, the final exam. It has to be kept under lock and key until the very, very end. You only use this set once to get a final honest grade for your model. And once you see the score, that's it. No going back to make changes. That would be cheating. And here's a really common way to carve up your data. A 70-15-15 split is a fantastic starting point. You get a big chunk, 70%, for learning. Then 15% for tuning on that mock exam, and that last precious 15% is saved for the final unbiased grade. Now, the exact percentages might change depending on your project, but the idea of these 3 distinct roles, that always stays the same. All right, so now that we get the why and the what of data splitting, let's get into the nitty-gritty how. Because it turns out just randomly chopping up your data isn't always the best move. The kind of data you have really changes how you should be splitting it.
You know, for a lot of projects, a simple 80-20 random split for your train and test sets is a totally solid default. It often works just fine. But what happens when your data has some hidden quirks? Let's look at a couple of really common situations where that simple approach can fail you.
Okay, picture this. You're building a fraud detection model. Fraud is, thankfully, pretty rare. Maybe it's only 1% of all your transactions. If you just split your data randomly, what happens if, just by pure bad luck, you end up with 0 fraud cases in your test set? How on earth are you supposed to know if your model is any good at finding fraud if there's no fraud to find?
The answer is something called stratified splitting, and this chart shows it beautifully. Stratification makes sure that the percentage of each category, in this case 99% not fraud and 1% fraud, is exactly the same in your test set as it is in your full data set. It guarantees a fair and representative test, so your model actually has a chance to learn from those rare but crucial examples.
So what about data that has time baked into it, like stock prices or weather forecasts? You absolutely cannot just shuffle it randomly. That would be like using information from tomorrow to predict yesterday. It makes no sense. For time series data, you have to split it chronologically. You train on the past and you test on the future. Period. Just like it works in real life.
Okay, I need you to listen closely for this next part. We have to talk about a really subtle but absolutely devastating mistake called data leakage. It's the silent killer of machine learning models. It can trick you into thinking your model is a work of genius when in reality, it's just been cheating the whole time. Data leakage is pretty much what it sounds like. It's when some piece of information from your secret, unseen test set accidentally spills over and contaminates your training process. When this happens, you get these amazing, wildly optimistic performance scores that will completely and utterly fall apart the second you try to use the model in the real world.
So how does this happen? Well, here's the number one culprit. Let's say you decide to scale your data, a super common pre-processing step, but you do it on the entire dataset before you split it. Uh-oh. By doing that, the math you use to scale your training data is now influenced by the values in your test data. You've basically peeked at the answers on the final exam before you even started studying. So what is the golden rule to prevent this disaster? It's so simple. Split your data first, always. Then, and only then, do you do any pre-processing steps like scaling. And here's the crucial part. You fit your scaler, meaning you learn the scaling parameters, using only the training data. Then you use that same scaler to transform both the training set and the test set. This is the only way to guarantee your test data stays 100% pure and unseen.
Okay, we have covered a ton of ground, so let's boil it all down into a simple, actionable checklist. Think of this as your blueprint for success that you can use on every single project to make sure you're doing this right every time.
Here it is, your must-do list. Number 1, always split your data before you do literally anything else. Number 2, if you're doing classification, especially with imbalanced classes, use stratified splits. No excuses. Number 3, got time series data? Use a time-based split and never ever shuffle it. Number 4, do all your model tuning on a validation set. The test set is not for practice runs. And finally, the most important rule. The test set is sacred. You keep it locked away and use it only once for that one final honest score. Follow these rules and I promise you, you will avoid so many of the most common and painful mistakes in machine learning.
So I'll leave you with this one question to think about for your own projects. When you look at your model's final score, are you confident that it's truly testing its ability to learn and generalize? Or have you maybe accidentally just created a really good guesser? Because proper data splitting, that's the only way to ever know for sure.